So, tough topic, right? GDTs are not super easy. We have learned that they do have a real good payoff, though, in understanding. So, we've gone through lots of lesson material, recitations, all that good stuff. How you feeling about them right now? Feeling better than you were starting off? Yeah, a lot better, a lot better. Comes with practice, right? So let's talk about this particular quiz and see how we do. So, first question was, describe in your own words the difference between circularity and cylindricity. What is the primary difference between those two geotolerances? Would you all say? Okay, absolutely. Whereas cylindricity is more like a what? 3D. For example, when you do the circularity, you're really just concerned about the circular shape at a section point location. Cylindricity, however, you're concerned about that circular shape from one end of the feature to the other. So that's where we get this whole issue, does it get outside of that shape and that sort of thing. So two key differences between the two. And circularity could obviously be used for holes, small holes in plates, probably a lot better than cylindricity could be used. Now, in theory, could they possibly really control the same thing? Yes. But there's still a preferred option between the two. Okay? So that makes sense. How about number 2? Can straightness tolerance be used on a cylinder? Yes or no? Definitely can. How can it though? Kind of give me a description. What can a straightness tolerance do for a cylinder? That's true. We could actually make the cylinder or the hole or the feature out of whack, going sideways, making a curve to it, all kinds of things. So it definitely can be used. All right, so here's a good one. Profile tolerance. Is it only used for curved lines and arcs, or can it be used for straight lines? Yep, it can be used for both straight lines and curved arcs. Although a lot of your descriptions and guides and teachings will involve shapes like this, when it shows it to you, it can be used to control a surface that has a lot of edges on it too. In fact, it's often used to do so. Okay, so on that same note, what's the primary difference between a profile of a line tolerance and a profile of a surface tolerance? What's the difference between when you give a feature when you're doing profile of a line versus profile of a surface? Well, you've got two different actual geotolerances. They show up as two different symbols on your list, right? Go open up your packet there and tell me what's the difference between the symbol for a profile of a line versus profile of a surface.
My understanding would be the lines or edges of the part would be the line, and then the surface would be like a flat.
That's a good way to say it. All right, so first question is, what do the shapes look like on my symbology? What's profile of a line symbol look like? Right there in your material. Just look at the chart. What shows up in the box?
It's like just a curve without the box.
Back like that, right? And then the surface is like this, correct? Am I right? Okay, so you all are on the right track. So profile of a line, let's say we are dealing with a plate or something. Profile of a line is very interested in controlling the shape through one side, one overall shape. Profile of a surface is interested in the same thing, except for it's concerned about it all the way through the part. So if this is the profile, it's concerned of that profile here and here and here and here across the part. So profile of a surface, basically saying it this way, if you have a part that is square and then has a rounded top, and we call that a profile, we are concerned about that rounded top all the way from the front of the part to the back of the part. Does that shape hold here, 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 and all the way back? See the difference? So you can probably assume that someone maybe do profile of a line if they're doing a flat plate system, but they might do profile of a surface if they're doing something that's elongated, a complex cylinder, complex shaft. An axle shaft would be an excellent example. Maybe it's got some spur gears or something to it. That would be an excellent example of when a person might end up using profile of a surface. Questions on that? Okay. So, on number 5 here, below is an image of a profile of a surface geotolerance feature control frame. But there is an unusual circle at the joint of the leader. What does this circle mean? What is that the symbol for right here?
All the way around.
All the way around. So it basically means all the surfaces around, right? So now this is also a welding symbol whenever you see the all around symbol. Yep, it's the same concept. All around. Now sometimes you'll see it as a solid dot versus a circle, but it means all around. Of course, it implies all around of the feature. So, a little crossover there, welding symbols. So, which geotolerance would be preferred for surface roughness issues or wavy imperfections? What geotolerance would I use for a condition like this?
Should be flatness.
It is. Flatness is an excellent choice for this. Can straightness be used? Possibly. Would it be the best choice? Not really. Okay, so number 7, reviewing the section, excuse me, section view below, you've got a part with 2 holes in it, hole A and hole B. If the designer is concerned about hole A being aligned with hole B, what geotolerance would you recommend? Yep.
I can think of 3. I mean,
Give me the one that you think is the best fit.
true position.
Parallelism. Although I see true position as being logical, but why does parallelism work better?
Makes them straight.
All the way across, right? True position has that extra controlling factor. Typically, true position is based on dimensional information. We're wanting the whole concept of one being aligned perfectly with the other. So if this one gets out of alignment, or vice versa, it doesn't meet. So by parallelism is probably the better choice. And then the rest is, graphical. So questions on that quiz you all want to ask? All right. So that's kind of the logic that you should expect with midterms based on this, of this question and answer, using your resources to figure it out and making good decisions. So that's what we're going for. Really, really thinking a lot about this stuff and how to apply it. But the best part is you get to use your resources. So keep that in mind. If you're going through and you're going through these packets and stuff and you've got notes, make more notes. Make little things that help trigger the thought process to make things connect for you. I like to draw little sketches all the time. So if it helps, do little doodles on your notes to help this thing make sense. Okay, now, switching gears. Any questions on your current assignment you want to ask? On the assignment, that's cool. Any questions or thoughts to kind of wrap up on geotolerancing and that sort of thing that you want to mention or ask about, clarify? Now's the time to knock it out. Not really. No, on computer applications, this section of it is all about you being able to interpret. Someone's giving you the information and you can interpret it. I'm not going to require you, maybe a hair if I do, but not much. That's a really good question. So we've been learning, especially today's blueprints, when someone designs a part, especially a big mass-produced part, they use the parametric modeling system to model the part in 3D, and then the computer generates all the necessary views and puts in information. The computer, however, has no ability to control or understand quality control. So the designer, although the computer will have like a little template or module for it to insert feature control frames and add them in, it's still going to be the designer who actually chooses what to use, where to use it, and what sizes tolerance zones need to be. So where the computer is already turning 3D models into drawings and adding dimensions very quick and easy, that's why CAD technology is kind of changing a lot. We don't really need to spend as much time on the blueprint side as we used to. It doesn't have the ability to be smart. Keep in mind that computers, no matter how great they are still just glorified calculators. They can only do what the designer has in mind. So it'll help you make a feature control frame, but you got to tell it what to put in that feature control frame. And that's why I always say, when you're thinking about this stuff, try to get your head in the mind of the designer who's putting the blueprint out there to figure out what they're trying to control. Think about what the part is used for, what it might be interacting with, and understanding why they put a geo tolerance here and the type they used. Other questions? Sounds straight up what it was like. Yeah, keep in mind that when you're dealing with cylinders, they will love to attach feature control frames to the sides that might describe the diameter. So if I were to give a straightness tolerance and attach it to this edge, a person might think I'm talking about this surface being straight. But in reality, what am I actually talking about being straight here?
Center line.
The center line. You can tell the difference because it's attached to the diameter value associated with this dimension. So again, they don't always give you those nice boxes with leaders attached to some specific surface. They do a lot of this right here where they attach the feature control frames to a dimension or something else that's already there and want you to figure out what that feature control frame is referencing. So one little trick. Yep.
So if they did for some reason want to put a straightness on that side there, they would go completely to the other side somewhere away from the diameter.
It's very unlikely that they would actually call out a straightness tolerance on a cylinder, on an edge. It's very unlikely that someone's going to say, hey, I want just this edge to be straight because it's a cylinder, right? Now, if it wasn't a cylinder and if it was just a block of wood, then yeah, they'll do this number here, point to an edge, or they'll have a dimension and they'll do it here. Now, how can I tell what's the difference between this dimension and the one I just had? Doesn't have a diameter, so and also you don't see what here in the middle? Center line. So you know this is not a cylinder, right? This is some kind of rectangular piece, which means this is an edge I can actually deal with. Whereas a cylinder, technically you're not dealing with an edge at any point. It's round, right? So if it doesn't have a center line and no diameter symbol here, yeah, they'll throw a feature control frame, point a line to it, put a straightness tolerance in, we're good to go. But if it's like what I had and there's a diameter symbol, you're not going to be able to control this edge. You're going to end up controlling the center line. Does that make sense? Two totally distinct differences. And it's all about whether or not you see this or if you see a hidden line there, or a center line there. Okay. Let's see, what else can throw you off? So yeah, again, on parts like this, it's great when they do this number and they put the feature control frame in, put an arrow and point to a surface, but just realize they're not going to do that a lot. There's just not enough. The real estate value of a sheet of a blueprint is pretty high. So if they can keep these feature control frames out in the way and not use a lot of these arrows, they're going to do that. Okay? Other questions? All right. Questions on the assignment? Anything else you want to ask about the assignment was? Before I switch gears. Not right now. Not right now. But more or less with a problem like that, it's just establishing datums and it's just showing the right tool. That's basically what it boils down to. All right. Going once, twice. Okay.